We saw how to draw a magnetic field line for a bar magnet. Actually, we can do the same for any given magnet. It's the same process. So what is that we observed? And what else we need to know about magnetic field lines? So I'm starting off with 1A, wherein we are looking at outside the magnet. So physically outside the magnet. So in this case, outside this white boundary, the magnetic field line starts at north. So we consider that the magnetic field line starts at north. Again, it's our consideration. Remember, this is all hypothetical, right? So these lines are hypothetical. So we consider that they start from north. So all the lines start from north and they end at south. Okay, I've not mentioned that, but they end at south. Inside the magnet, so inside the physical magnet, the magnetic field line starts from south. Remember, so the magnetic field line starts from south over here. Outside the magnet, it starts from north. Okay, this is must to know. No two magnetic field line crosses each other. So as you can see, I have few magnetic field lines. Say a magnetic field line starts over here. This cannot happen. Okay, so it can go like this and occupy pass through this space and all of that and end up in this manner. But it can never cross like this. Okay, and this is also not possible. This is possible, and again, the space is it's kind of very small space, so I can't draw. But yes, you can imagine in this space we can have n number of magnetic field lines. So combining all of this, we have the third point, that is magnetic field lines are continuous and unbroken. So outside it starts from north and ends at south. Inside it starts from south, ends at north. And since no two magnetic field lines are crossing each other, so given a magnetic field line, it will go one, not a circle actually. I was able to tell a circle. It'll just complete a loop. So it's always continuous and unbroken. So the fourth point is more the magnetic field line density, more the strength. That is, if you see a space, right? So if you consider a space something like this and some space like this. Okay, again, the space has to be same actually. Yeah. So if you consider space like this and similar area space like this. So clearly the density is more over here than over here. So the strength is more over here. So more the magnetic field lines in a given space, more the strength. Okay, again, it's quite simple. So if you see see here, it is a lot more compared to A and B, if I call this as C. So the strength over here is more than A or B, and strength in B is more than A. Next point, inside a magnet, magnetic field lines are uniform, equally dense, directed in the same direction. So the direction is obviously from north to south. Sorry, south to north inside. So inside a magnet, the magnetic field lines are uniform. Uniform means what? Equally spaced. That is equal density. It's one and the same. Uniform means it's uniformly spread means they're equally spread means equally dense. So you can see here, if you take any space, the same area, you can find the same number of magnetic field line crossing through it. So equally spaced, equally dense, directed in the same direction. That's your fifth point. So what does it mean? When you look at something like this, wherein you're telling the magnetic field line density is equal, right? What does it mean? It means that the strength is equal throughout or uniform throughout. So wherever you see the strength of magnetic field lines in this space, the strength is equal. Okay. So how do we draw it? As I've shown you guys, this is how you show an uniformly dense magnetic field lines. Okay. Again, this is also part of your syllabus. Whatever you are seeing from past few videos is part of your syllabus. All the points has to be remembered. So since we have magnetic field lines which are uniform, obviously non-uniform magnetic field lines are there, right? So pretty much over here is non-uniform, this and everything, right? These are non-uniform. Okay, few more example over here. This space is non-uniform. All of this space is non-uniform because they are not equally dense, right? So there might be three magnetic field lines, but here they spread out this side and here they are closed in. And this is also a magnetic field lines which are non-uniform. Here the density is more, here the density is less, even lesser. Okay, so here strength A is high compared to B, and C, strength B, the magnetic field strength in B is higher than compared to C. So this is an example of non-uniform magnetic field. And the density talks about the strength, remember. Okay, all of these points are important to remember. Let me erase all of this. Yes, you guys have to copy all of this point with the diagram, which helps you guys to understand and recall, right? Diagram helps you understand and recall things easily. So do the same as I've done. So please pause and write this down. And same over here, please pause and write it off. Okay, one last time. Magnetic field line outside any given magnet starts from north and ends at south. Inside it starts from south, ends at north. Okay, it's the opposite. That you guys have to remember. So this is opposite of each other. No two magnetic field line crosses each other. Second point. Third point is it's always continuous and unbroken. So if you have two magnetic field lines which are not crossing each other and you have north to south and south to north, obviously it can have a property which is continuous and unbroken, right? Makes sense. So the density, the field line density talks about the strength of a given magnet. Again, remember, these are hypothetical, it's our own imagination, right? It's not observed in nature that you have lines going across. So for a given diagram, I can draw many lines as possible. It's not that I have to limit it to this many. I can increase this as well. So remember that. So given a diagram, look at the number of field lines for a given space, maybe 1 centimeter square or 1 meter square if possible. So in that space, if you see equal number of number of field lines and equally spaced, then you can tell the strength are equal. Okay, so that's one thing. And next is inside a magnet, the field lines are uniform, equally dense, directed in the same direction. So this means that you'll end up with a diagram like this. So wherein you have magnetic field lines running in the same direction and have the same strength throughout. Anywhere you take, they have the same strength. So this is your uniform magnetic field. And non-uniform is wherein you don't have same number of magnetic field lines around and there is unequal magnetic field line distributed across.